This video is going to cover shear and moment equations in terms of x. This is the problem that we're going to be starting off with to solve, but before we get there, let's talk first about how to solve for shear and moment equations in terms of x. This is literally the exact same thing as equilibrium of a deformable body. The difference is instead of knowing the exact point that we're going to make the cut and find the internal reaction forces, say point C, and instead of knowing the exact distance to it, we're literally just going to say somewhere within this first region, we're going to make a cut. Somewhere within the second region, we'll make a cut. Somewhere within the third region, and somewhere within the fourth region. The exact distances we don't know, nor do we care, because it's going to be in terms of the distance x. That's the only difference that's going on here. So instead of knowing the exact distance, it's just a variable. That does somehow make things a little bit scary, but it's really actually not too terrible. This is a ridiculous problem, as I found out while solving it. Step number one, though, is always to find your reaction forces. So I went ahead and did that for you guys. I believe you can figure out how to do statics at this point. So let's go with you could find these reaction forces. So next up is to determine which direction is x. So x, it kind of depends. It could either be left or right, just like when we were doing equilibrium of a deformable body, we could choose to either take a cut from the right or we could take a cut from the left. You know, look at the free body diagram on the left or on the right. So I'm going to start with x coming over here from the left, going in the positive x direction as usual. But I really don't want to go too far with this one because those distributed loads just really aren't looking very fun. So I do know that I can go the other way as well. Yes, if I just want to take the other side, maybe I want to take the right free body diagram instead of the left, I can most certainly do so. So I have two different directions I can come from for x, x1 and x2. I get to choose which one I want to use kind of as I please, but obviously they're going to be getting increasingly more difficult as we get to the center. So now that I've done that, now we need to make a cut every single time there's a change in loading. So there is a change in loading. There was a positive, 300 kips going up, and then all of a sudden we have this distributed force, so anywhere in here is a really good spot. It's going to constantly be doing that. The next actual change would be at this spot, where all of a sudden we have a flat 25 kilonewtons per meter distributed load instead. So there's the change. We went from linearly distributed to that flat line distributed one. So that will be our first cut. We'll call that cut 1. It'll be somewhere in there. Then, of course, we do have a distributed load, but then there's this change in loading here, so we have to cut before we get to that load. We'll call this one cut 2. Then after we have that point load, then there's more distributed loading, so that's going to be cut 3 before we end it. And then after the distributed load, we have nothing until we have this point moment. So yes, there's going to be yet one more cut, so we'll call that cut 4. Now in terms of do I have to solve them as 1, 2, 3, then 4, technically the answer is no, I can solve them in any order. But if you're going to start on the left side, you keep going left until you're done going left, and then you start from the right side and keep going from there. So we're going to either start here with x1 and work our way this way, and when we get done with that, we're going to start with x2 and work our way that way. That's effectively what we're going to do. So let's see it in action. First up, now that we've made all of our cuts, imagined all of our cuts really, we're going to analyze just like before, one cut at a time. Yes, one cut at a time. So we're going to start with cut number 1. And cut number 1, I'm going to use x1. I'm going to use x1. So since I've decided I'm going to use x1, I need to state how much of x1 I'm going for cut number 1. So cut number 1 does start at 0, right? Does start at 0 meters from x1. And this equation is going to satisfy all the way up to, again, we said right here at that 6 meters. So we're going to go all the way to 6 meters. So now we're going to draw a free body diagram. Gotta love free body diagrams. So it doesn't have to be a massive free body diagram, right? Because it's anywhere between 0 and 6 meters. It could be the tiniest few meters of your life, not even a meter. Doesn't really matter. So it is just a linearly distributed load. And we do have our very beautiful point load. This is 30 kilonewtons of the point load. The distributed is, we're going to figure that out. And the distance that we've gone so far is, again, just x1. Now, again, this isn't really too different from when we said, you know, oh, point C is over here 4 meters away from the end, and you were like, oh yeah, x1 is just 4. That's literally the only difference, is we've replaced the actual distance that we know we were going with a variable instead. So it's not too terrible. We are going to have our internal shear, and we're going to call it shear 1 because it's at cut 1. And then moment, we're going to call that moment 1. Make sure you are drawing it in the positive sign convention directions. Make sure you do that. Next up, we definitely need to know what is that W? What is that value for the uniformly or linearly distributed load? So there's kind of two ways of doing this. You could do some similar triangles, right? You could draw a similar triangle. You could say, well, W is to x1 as the whole thing, which we said was 25 is to 6 meters. And you can kind of solve for that. You might be thinking, well, I'm going to get W here in terms of x. Yes, remember everything's supposed to be in terms of x. So we have W over x1 is equal to 25 over 6. So we're going to get that W is equal to 25 over 6 times x1. That is obviously similar triangles. You could definitely do that. The other way to do this is to look at that line. Know that it's a line. Remember that the equation of a line is y equals mx plus b. And b, well, the intercept, we're starting at 0, so let's just call him 0. So it's literally just the equation of the line is just y equals mx, right? So what is the slope of the line? What is m? Again, m is literally just rise over run. So we rose upward, how far? 25 over a run of 6. Hence why it's rise over run times x, right? That is literally the equation of the line, slope times x. So yes, you could do similar triangles, right? As we just proved, there it is, 25 over 6 x1. Or you could just look at it and go, wow, I know the slope of a line. It is the rise over the run. However you want to do it, we get the same answer. Just going to get rid of that. So W over here is 25 over 6, again, times x1. Yes, so our variable is kind of floating up here. x1 is in 2 spots. It is part of the height of that linearly distributed load, and it is also the distance horizontally that we are going. Yes, so you can see that this isn't going to start off very fun, and it's not really going to get too much better than this. But how do we solve for shear and moment? We simply solve for shear by summing for the forces in the y direction and setting them equal to 0. So what do we got going on? We got, well, we should maybe do this in colors because we can. We have 30 kilonewtons going up. Definitely write your units. I know when you are doing this, you don't want to write units. It is really annoying to constantly write kilonewtons, meters, blah, blah, blah. But if you don't write your units, this is definitely where you're going to make a mistake. If you didn't already make a mistake with equilibrium of a deformable body, you are 100% going to make a mistake here because you're going to forget if you've multiplied by enough distances, and it's going to get pretty terrible, as you're going to see here. So we have 30 kilonewtons going up. Then we're going to change directions. We've got our minus. We need to know the area under the curve. So the area of a triangle is 1/2. What's the base? The base of the triangle is just x1. Again, this is in meters, by the way. And the height of this lovely triangle is 25 over 6 times x1. But this is in kilonewtons per meter. So again, the whole reason we're going to write out all of these units is so that we can go back through with our lovely red pen and just cross out our units, watch them cancel, make sure that the final value that you are getting is in fact the correct unit. So we are getting kilonewtons, so good. And then last but not least, we also still have shear going down. So if it needs to be said, we were summing where up was positive. So this is going to be shear 1. So I'm just going to pick up and move V1 to the other side. So I have V1 is equal to 30 minus, we have 25 over 12 x1 squared. That is a very delicious thing. Again, don't forget your units is in kilonewtons. It's looking delicious already. Now remember that if the load is a 1 degree, the shear is a 2 degree, and yes, this is in fact a 2 degree polynomial. That is a good thing. That means our moment is going to be a 3 degree. So let's figure out that one. So again, we have some of the moments. Always take it about the cut. That's a really great idea. So we're going to go counterclockwise positive. So what do we have? Well, we do have the 30 kilonewtons. So 30 kilonewtons times what distance? That distance to the cut, oh, this is negative direction, by the way. We're negative. We're going to be going around the cut that way. That is definitely the negative direction. So times its distance, x1 meters. Then we have kilonewton meters. Now we're going to do the distributed load. The distributed load, first up, force. The force of this distributed load is going to be the area under the curve. 1/2. The base is x1 in meters. The height is 25 over 6 x1. And this is in kilonewtons per meter. So again, those are going to cancel out. Right, those meters are canceling. We're in kilonewtons. Kilonewtons is not moment. So what we have right now is that the force is going to be at that centroid. How far is that centroid from the cut? How far is it from the cut? Again, it's 1/3 to the close end. But what's that distance? So this one is going to be times a beautiful 1/3 of the base again being x1. Delicious, isn't it? And again, this is in meters. So now we have kilonewtons times meters. Good. And then there is moment 1. So then we have m1. m1's going to be going in the positive direction. So yay, there we go, plus m1. That is lovely, isn't it? Absolutely lovely. It's really not. It's a really disgusting equation. We all know it. So this means, waving the hand, doing the magic here, we're going to kind of shorten this up, and I'm just going to tell you the final answer here. The final answer is 30x1 minus 25 over 36 x1 cubed. This is in kilonewton meters. Delicious. So one thing about shear and moment equations in terms of x kind of goes back to the actual diagrams themselves and how they're created. Remember that we take load and we find area under the curve and we get shear. For us, what we did here with moment is we did the shear, find the area under the curve of the shear to get moment. When we're talking area under a curve, we are literally talking integrals. So effectively we're doing calculus without the nasty integral and derivative sign. So all those things we talked about for the diagrams, for shear moment diagrams, those were literally just calculus put into words. And it's not very pretty. But long story short, if you take the integral of the shear, you're going to get the moment. Vice versa, if you take the derivative with respect to x of the moment, you're going to get the shear. Now, there's a little caveat about this. It pretty much only works if you're going left to right. Okay, it kind of works if you go right to left. So what I'm really saying is that this is literally only going to work for our x1 direction. If you go in the x2 direction, you may or may not have it work. So if you always go left to right, it will always check out. Sometimes you're going to be like, whoa, the sign's a little bit backwards if you're going in the x2 direction. And again, that's just because you're effectively trying to draw the shear and moment diagram in reverse. And we had a big thing about please only go left to right. And that is literally because that's going to make the calculus actually make sense. So if we take the derivative of our moment equation, right? You take the derivative of 30x1, you're going to get 30. You take the derivative of negative 25 over 36 times x cubed, you're going to get 3 times 25 over 36 x squared, which is 25 over 12 x squared. So yes, this does actually check out. And this is the only time we're going to do that because at this point, I will tell you that I went through and I attempted to work out the problem with cut 2 going from the x1 direction. And oh boy, that's a really nasty one. That is a really, really nasty one. So let's not do that. Even I looked at that equation and I said, no, that's a bit much. It was a little bit too many parentheses and parentheses, and it's just straight up gross. So I'm not going to do cut 2, actually. I'm going to say no more in the x1 direction. Let's start in the x2 direction, which does mean that what I'm going to start doing now is I'm going to start going this way, and the first thing I'm going to hit is cut number 4. So I started with cut number 1, then I'm going to jump to cut number 4. Is that a bad thing? No, it's really not. So let's draw it out here. We're going to have cut 4. So we are jumping the gun a little bit. Before we do cut 4, we do need to talk about what is the distance. What is it going to cover? We're now doing x2, so we're going to go from 0 to x2 to how far? Cut 4 goes anywhere from 0 to all the way to here, which is 4 meters. It's really important for you to write these down because you're going to have so many different equations that eventually you might get them confused as to which one is which, and also which direction you're going. So make sure that you're writing these out. Now let's draw our beam. This one is so simple. Here we have our little x2 distance, and we are just given this very lovely 60 kilonewton meter point load on the end. That's all that's happening in that cut. That is absolutely beautiful. So now let's draw on our shear. Shear goes up on this side, by the way. It's not 2, it's number 4. Gotta get that right. And moment goes around the other way as well, so that's moment again 4. So okay, this is gonna be lovely. This is the best one to do. If we sum our forces in the y direction, set it equal to 0, you'll notice that there are no forces. That's not shear 4. Yes, there are none. Isn't that cool? Which means that if you were to graph this out, currently there is no change in shear at the very end. There is absolutely no shear in that beam at the very end, which is kind of cool, honestly. It's kind of cool. In case you're wondering what that would look like if we were doing our diagram, we're way over here at this, this end. If your diagram has literally got nothing going on, you put a little 0 there, a little 0 at that side, technically you can just put a giant 0 in the middle. Let everybody know, hey, there is nothing happening on that one. Just a little thing how we do it in the engineering field. Next up, we're going to do the moment. So we're going to take the sum of the moments about the cut. Counterclockwise is positive. So what do we have? Well, we have M4. He's going the wrong way, so minus M4. And also 60 is going the wrong way, so minus 60. Should have done those in the correct colors. Kind of do that. There we go, minus 60. Again, this is kilonewton meters on him. So lo and behold, M4 is equal to minus 60 kilonewton meters. Unfortunately, this was the only nice cut that we're going to make the entire time. So conveniently, it does work out. If you take the derivative of -60, you do get 0. So yay, sometimes it works. Sometimes when you're going on this side. Not always, though. So the next one that we're going to get when we are going in this direction, again, we're going to go from right to left. So we already did cut 4, so we're going to bypass him, and we're going to get over here. Next one up is cut 3. Cut 3 and cut 2, they're absolutely disgusting. There is no way around that. So we're going to draw him out. So we're starting that distributed load. So we're going to do cut 3 this time. I was hoping I could write that fast enough, but not. Cut 3 again, where does he go? We pick up from 4 meters, right? Because we just wrote it in terms of 0 to 4, right above. That was cut 4. So cut number 3 is starting at 4 meters and finishing at 4 plus 2 is 6 meters. So this one's going to go from 4 to x2 to 6 meters. Again, definitely good to watch for that. Definitely good to watch for these. So let's draw that pretty little picture. What does it look like? We have our very beautiful 60 kilonewton meters hanging off the end. And then we have some of our distributed load. And that distributed load, again, does have a height of 25 kilonewtons per meter. Just as a reminder, it is 4 meters to where that distributed load starts. However, x2 is the whole distance. And honestly, this is where it starts to get not quite so fun, is when we're doing things that very, very, very lovely little distance calculation here with x2 being the full distance, but you don't want the full distance, you want a piece of it. That's where everything's going to start to come back to bite us. So shear goes up, shear 3 goes up, and moment 3 goes clockwise. All right, let's have fun. Those are our diagrams so far, so let's enjoy the math and see where it takes us. So we're going to sum the forces in the y direction and set it equal to 0. Again, my up direction is positive. So we've got shear 3 going up. Ain't that swell? Then we have our minus our 25 kilonewtons per meter across how many meters? That's the good question. Across how much? Well, it's not fully x2, right? Because x2 is this distance. It's not that. It's only this much. So what is that much? Well, that much is going to be x2 minus 4. Right? x2 minus 4 in meters. That's going to give me that little highlighted area. So you can start to see where this is going to get disgusting. Shear, obviously not too bad, right? The shear equation, because that's all that we got going on, shear 3 is going to be equal to 25x2 minus 100. That's in kilonewtons. Okay, so that's really not too terrible. That one was not bad. You might be wondering, where does it start to get bad? Well, the moment equation. It's never really about the shear. It's always about the moment. The moment's where it gets disgusting. So let's set up this moment. So we're going to sum the moments about the cut. Unfortunate as this starts to sound. So we're going to sum the moment about the cut, set it equal to 0. What do we have? Well, we do have that moment 3 is going in the wrong direction. So we have minus moment 3. That's a great start of things. Then we have that lovely distributed load, and he's also going in the wrong direction. So it's minus, again, what's the force? The force is going to be the 25 kilonewtons per meter times, we already just discovered what the distance was, right? It was x2 minus 4 meters. Again, that was literally right here. So that's force, as we found. We just cross out our meters here. That's force. What's the distance? And we want the distance from the centroid over to the cut. So that distance is 1/2 of the distance that we literally just had for this little green highlight area. So that is half of x2 minus 4. Yes, that is in meters. And now you can see how disgusting this just got. And then don't forget, we've also got the 60 over here floating on the end. He's also going in the negative direction. So yay, negative 60. But, you know, gloriously, he's actually in kilonewton meters. That's actually kind of cute. So this one is disgusting. There is absolutely nothing nice about this one. Long story short, we'll just cut to the chase, and I'm going to tell you that it took me quite some time to solve all this stuff, so I'm going to not put you through that. But moment 3 boils down to, left everything in terms of a half, please forgive me, 25 over 2 x2 squared plus 200 divided by 2. In case you're wondering why this is happening, I took the 2 and I pulled it out. So everything's got this half thing going on. So 200 over 2 times x2 minus, truly it makes a lot more sense if you do it all by itself. This is 520 divided by 2 kilonewton meters. So again, if I were to take the derivative, this is where it gets funky, right? If I take the derivative of this, those 2's cancel, I have negative 25. This is not negative 25, but again, we're going the wrong direction, so we'll take it with a grain of salt. Then we have the derivative of this guy, who that is 100x2, and we have minus 100. So again, sign-wise, slightly different. Numerically, still the same, and the derivative of a constant is just, yep, 0. So technically, yes, kind of, sort of. Signs are a little bit different, and that's just because of the direction that we're going. We're going the wrong way to make a shear moment diagram. So there it is. There's the nastiness. That is moment 3. He doesn't actually look as bad, truthfully, when you've solved for him, but this, not very fun, let me tell you. So the next thing that we have, again, we started here. We've gone through cut 4. We've gone through cut 3. We've got, lastly, cut 2. And he is definitely not making it any better, right? He's the same thing that we just did and more. Yes, so cut number 2 finally. Again, where does he go? He starts at where cut 3 left off. That's 6 meters. And he finishes at 4 plus 2 plus 2. That's going to be 8 meters. So 6 meters all the way to 8 meters, that's going to be x2. So let's get that free body diagram going. Well, that one's going at an angle, but it is what it is. We've got, let's see, we've got our 60 kilonewton meters over here. We've got our distributed load. Yep, there he is. Again, I just want to put, I guess I'll put it in blue here. Remember that this is technically 4 meters between those two. And then we've got our point load. I'm going to draw it a little bit more over here just to make sure that we know what we're looking at. This is 145 kilonewtons. And again, the distance from this guy to this is 2 meters. And the whole thing here is x. All right, this is x2. Delicious. Now we're going to throw on our shears and our moments. So again, shear goes up. This is V2, finally at cut 2. And moment goes clockwise, M2. Woo! So it's actually, for the shear equation, not that much worse. The moment equation actually isn't that much worse because we get to reuse what we already did. So it's not as bad as I was making it out to be. Moment 3, though, was absolute terrible. So we're going to sum the forces in the y direction, set it equal to 0. We're going to take up to be positive. What do we got going on? Well, we've got shear 2. And then we've also got plus the 145. I'm going to just throw him in because I got my color on it. Then, oops, that's 25 kilonewtons per meter. And so now the distributed load. The distributed load is, scooch that over, minus 25, this is kilonewtons per meter. What's the distance? Now you might be thinking, ooh, this one got really disgusting. It didn't change. Believe it or not, it did not change, because look at this. The distance it is this much. This distance is still x2 minus 4. It actually didn't change. So that's kind of adorable. So again, the distance is x2 minus 4 in meters. So the actual only thing that changed from our last cut to this one was we just shunted in this 145. So that's actually not too terrible. So our shear 2 is going to equal 25 x2, it's an ugly 2, minus 245 kilonewtons. So again, what happened? We are just, as you can see, 145 difference. That's it. That's literally all that happened. So now what we're going to do is we're going to sum the moments about the cut, set that equal to 0. Counterclockwise is going to be positive. We're going to do the same thing. So again, what's going on? We've got minus m2. Then let's do the green one. Let's do our green load here. We've got him going in the positive direction. Yes, actually, he's positive, so he's 145. What's his distance? His distance, we're just going to highlight it out here. His distance is this one right here. That is going to be the total x2 minus 4 minus 2. So x2 minus 6. That's going to be our distance. So x2 minus 6, that's in meters. He was in kilonewtons. Should always label all of our stuff. Don't be bad. So he's kilonewton meters, so that's good. He's our newest addition. Now we're going to do our distributed load. So our distributed load, again, the force, minus 25 kilonewtons per meter. Across what length? That length we said just literally right before it was x2 minus 4 in meters, right? This force is this force. We know force. We don't want force for this. We want moment. So again, it's force times the distance. So how far away is this centroid to over there? Well, guess what? It didn't change. It didn't change. It is still, if you call this distance x2 minus 4, you need to divide that by 2. Yep, it actually didn't change. So whereas that might have at first thought to be, ooh, that's going to be disgusting, it's not. It is still x2 minus 4 divided by 2. And you know what that is? Let me show you. Let me give you a nice sneak peek here. This is right here. Yep, and the only thing that we have left to add is just, yep, minus 60. So in fact, as disgusting as this whole entire equation is, the only thing that changed from M2 to M3 is this little bit right here. So we're going to take our same thing that we had for M3, rewrite it for M2, but adding in our little 145 times x2 minus 6. And what we finish off with is minus 25 divided by 2, x2 squared, plus 490 divided by 2, x2, minus 2,260 divided by 2. And again, if you're wondering why I have everything divided by 2, you do the math. I pulled that homie to the front over here and then did all that glorious stuff. So you can solve for it. You'll get the same exact thing as me. So there you go. It's not beautiful, let me tell you. So are we done? I mean, technically, we have shear and moment for all 4 cuts. However, are we correct? Are we correct? How do we know if we're correct? How we know if we're correct is if when these two, when x1 meets x2, are they the same? Are they the same? If they're not the same, we done messed up. So let's find out how far did we go with x1? We went to 6 meters. How far did we go with x2? We went to 8 meters, which is again at the same spot. So you can see we have an equation written for the same spot, but we have 2 effectively different equations. So the last thing that we need to do is we definitely need to check continuity. All right, we definitely want to check this continuity. So the continuity for us is when x1 is equal to 6 meters and x2 is equal to 8 meters. So remember, I made you write out these equations, and I told you they're really useful because obviously there's the x1 equation where we can plug in 6. 8 does not exist between 0 and 4. 8 does still not exist between 4 and 6. But 8 does exist between 6 and 8. So we have to use cut 1 and cut 2. You should be able to look at your cuts on your free body diagram and see that. But again, if you're not paying attention because you didn't label your stuff right, you need to make sure you're picking the right equations. So we're going to check it for shear and moment at these values. So first one we're going to do shear 1. And this is for x1 is equal to 6 meters. So I'm going to plug in wherever x1 is, 6 meters. So I'm going to use, we'll highlight it here, I'm going to use this equation. So we've got 30 minus 25 over 12 times, it's x1, so it's 6 squared. Punch that in and you're going to get negative 45. Okay, what about for x2? x2, we need to use this equation right here. 25 x2 minus 245. So we have for shear at 2, this is x2 is equal to 8. We had 25 times x2, that's 8, minus 245, that's a big number. What do you get? Minus 45. This and this are the same. That's good. Now let's check the moment. Yes, they're nasty little equations, but we're going to check them anyway. So we got moment 1. We're going to swap to another fun color here. How about this orange? So we're doing this moment 1 equation right here. So moment 1, again, this is x1 is equal to 6 meters. So we're going to plug in. We have 30 times x, that's 6, minus 25 over 36 times our x, which is 6 cubed. You're going to get, believe it or not, only 30. Yeah, only 30. This is kilonewton meters. If anybody's wondering about our units here, you should definitely keep up with those. And lastly, we need moment 2 when x2 is equal to 8 meters. So again, moment 2, not a very glamorous equation, but here he is. Yeah, that's pretty nasty, and we're hoping for 30. We're hoping for 30. So we have minus 25 divided by 2 times x2 squared, so that's 8 squared, plus 490 divided by 2 times x, which is 8, minus 2260 divided by 2, And yes, if you actually plug that into your calculator, go ahead, give it a whirl just for me, and you're going to find 30 kilonewton meters. And those two are the same, which means it worked. Technically, you could do this at every single one of these ones, right? Where you had 4 here, you had 4 here. They should give you the same number unless you have a concentrated point load or a concentrated point moment. Because when you're doing these cuts, if you do have a concentrated point load, your cut goes right up to it but does not include it. So your X value, let's say that was X1 if you're coming from the end of the beam. And if you decided you wanted to come from the other side, let's say you're going to come from the other side of the beam, your X2 is this way. X2 also stops just short of it. So if you're X1, you're coming just short of it, and your X2 is coming just short of it. So what's going to happen in this case is you're going to have one value for shear and a different value for shear, and they're not going to be the same, and they're going to be off by exactly this number. If they're not off by exactly that number, then you screwed up. Your moments, however, in this case would be exactly the same. And the same thing's going to go for a point moment. Your shears will match up. So if this guy here was a point moment instead, your shears would be the same, but your moments would not be the same. And they would be off by, again, this value. So point loads, point moments, you do have to just watch out for them. When you do your continuity check, it will just be a little bit different. But other than that, everything should be the exact same. So if you're wondering how you go from these shear moment equations in terms of X into plotting this, all you got to do is just pick values. Effectively, what you're going to do is you're just going to plug in a number and plot the points. So for this example, this beam is a total of 14 meters. Maybe I'm just going to pick, I'm going to go every 1 meter and I'm going to place dots, and then I'm going to connect the dots, in whatever magical fashion to get my shear and my moments. Is it glamorous? Not really. Does it work? Sure. But there are definitely better methods to do plotting than it is to get these shear moment equations of X. But that's how we do them. And the reason that we do them is in case you have a really funky looking shear diagram. Like, for instance, this one's going to start off beautiful. Our shear diagram, it's going to go up. It'll be at 30. And then it's going to go down, 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 down. But it's not going to be going straight. It's going to be going at a 2 degree. And then it's going to go linearly and so on and so forth. The joy comes when now you want to go from your shear to your moment. You need this X value. And it's not like you can really use similar triangles for that. In fact, the best way to find this X value is to find your shear moment equation in terms of X. Because this exists all inside cut 1. Right? Cut 1 went from the start of the distributed load to the end of this distributed load, this linearly distributed load. So cut 1 was that. So if I want to find this spot right here where it crosses 0, all I need to do is take that shear equation in terms of X, and I'm going to set shear equal to 0, because that's what's happening. Where my shear crosses 0, where it equals 0, that's going to then give me X. So I'm going to set shear to 0, so I'll have 0 equals, in this case, I would have 0 is equal to 30 minus 25 over 12, x1 squared. So we're going to just move that to the other side. So we'll have 25 divided by 12, x1 squared is equal to 30 multiply by 12, divide by 25. And we're going to get that x1 squared is equal to 14.4. Take the square root of 14.4. You would think that that was going to be beautiful, and it wasn't. It was actually x1 is equal to 3.79 something 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 meters. But now that you have x1 is equal to 3.79 something something meters, now you can actually take the area under the curve and plot the moment diagram. So whereas these might not seem fun, and graphically you might be thinking, who in the right mind is actually going to draw this graphically? There is a reason for it, and that reason is to help you anytime that you have this very fun situation going on here. So anytime that squared shear diagram, this is the 2 degree, right? This 2 degree shear diagram is going to cross the 0. You want to make your moment equation and your shear equation in terms of x, because that's, honest to God, literally going to be the best way to solve for it. So I hope that you don't hate these too much. They're not exactly fun, but they're not too hard. They're just a little bit tedious. But I hope that helps you solve these types of problems.